So you may also recall that in Gen Chem 1, we asked you to skip ahead to Chapter 10 and do the first couple sections. So learning about some of the intermolecular forces, properties of liquids, and that was about as far as we went in Gen Chem 1. In Gen Chem 2, we're going to pick up with some of the later sections, but again, the idea is that you still remember some of what we talk about when we're doing intermolecular forces, because it's going to inform phase transitions, other things that have energy associated with them. So the reminder then is that inter means between molecules. So intermolecular forces are the attractive forces between two different molecules. Intra means within. Intramurals means that you have a competition within the college. And so intramolecular means we're talking about interactions, attractions within the molecule, between atoms making up the molecule. So they've diagrammed that here. Intermolecular are things like this interaction between a chlorine on one molecule and a hydrogen on another molecule, whereas this covalent bond between a hydrogen and chlorine in one molecule is an intramolecular attraction. So we want to focus on intermolecular forces in this chapter. You may also recall from Gen Chem 1 that we talked about a continuum of attractions, right? The strongest attractions we had were our ionic bonds. We had polar covalent bonds, which were kind of along this interface. Pure covalent bonds, a little bit weaker. And then we switched over to the intermolecular forces. We talked briefly about hydrogen bonds. So we're going to make sure that we talk about some of the other things beyond hydrogen bonds. We also have ion dipole, dipole-dipole, and dispersion or London dispersion forces. And that's from the strongest hydrogen bonds down to the weakest dispersion forces. All right, intermolecular forces. We just said relative strengths. Hydrogen bonds are going to be the strongest of the intermolecular forces. Ion dipole are strong, but not as strong as hydrogen bonding. Dipole-dipole attractions are relatively weak, and then London dispersion forces are going to be the weakest. Now you can consider intermolecular forces between any two different molecules, or you could just consider intermolecular forces between molecules of the same type. So they might say, given a pure sample of this compound, what type of intermolecular forces would you expect? And so you just look at one copy of that next to a copy of itself and say, okay, what kind of interactions can these things have? Or they might say, okay, mix these two things together, and when they mix together, what type of interactions can you have between these two different types of molecules? Because there's a range in strength, that is going to affect how attracted these two molecules are to each other. And if we're talking about a pure substance, we're talking about how much energy is keeping them together, and how much energy would you have to invest in order to get them to split apart. So to go from a liquid to a gas, what you're really doing is putting in enough energy to disrupt the attractive force between those two things so one can float up into the gas phase. Another thing to consider is that not all molecules are going to experience all the types of intermolecular forces that are listed up there. There are plenty of molecules that cannot do hydrogen bonding. You may recall from Gen Chem 1, there were specific requirements for hydrogen bonding. So let's start at the weakest. London dispersion forces are also referred to as induced dipole interactions, and that's because neither one of them has a standing dipole. It just so happens that if they bump into each other at some frequency, that bumping into each other induces a dipole in one of them. When it has that temporary dipole, it induces a dipole in the next molecule. So over here we have no dipoles. But when they bump into each other, we end up with an induced dipole between these two. Okay? So dipole, if you recall, we could describe with our dipole arrow, where that plus is saying this is the thing that is more positive, and the arrow pointing at the thing that's more negative, that gets to hold on to those electrons just a little bit more closely. We can also describe it in terms of that little delta plus, little delta minus. So if it's hard to see on this slide, that's where the little deltas are. So when this one molecule adopts a dipole for a fleeting second, if it's near something else, this negative side over here will make something that doesn't have a dipole want to have a dipole for just a second. And so it's temporary, it's induced. This is the weakest of interactions, because it's not happening all the time. London dispersion forces exist between all molecules. So this is the weakest, and everybody gets it. Even though it's weak, it gets stronger as you have more surface area in contact between molecules. So as the size, as the molecular mass, as the molecular weight of a compound gets bigger, that attraction is going to grow. So which of these pure molecules has the highest London dispersion forces? If you're looking at a periodic table, fluorine is at the top of the halogens, then it's chlorine, then we have bromine, and we have iodine as we go down that column. So they're getting from lowest mass to highest mass. So which one is going to have the strongest London dispersion forces? The iodine, right? The mass got bigger, the molecules got bigger, and so at room temperature, iodine is actually a liquid. Because it is attracted to itself the most, actually I believe that's a solid. So because it's attracted to itself the most at room temperature, it will actually form strong enough attractions to be a solid at room temperature. What about fluorine? At room temperature, what is fluorine? State of matter. It's a gas. Fluorine gas, chlorine gas. So because they are smaller, they do not have strong enough dispersion forces to be locked into a solid state at room temperature. Bromine, bigger than chlorine, smaller than iodine, is actually a liquid at room temperature, or temperatures thereabout. And that's because it's a little bit bigger than chlorine, it has more attraction, so it's able to get a little bit locked in and then kind of wiggle around like a liquid would, like little particles in a liquid. But it's not locked into a solid structure like iodine. So that's one of the columns on the periodic table where you can actually see the effects of dispersion forces in the diatomic molecules. Okay? So gas, gas, liquid, solid. Increasing molecular weight leads to increased dispersion forces, which lock them into a solid state at room temperature. So if we consider these molecules up here, neopentane, isopentane, N-pentane, they all have the same molecular weight, but they have different structures. Which of these would you predict would have the highest dispersion forces?
The N-pentane.
Which one?
The N-pentane.
N-pentane? So why is that?
Its surface area is the largest.
Has a large surface area, right? It can bump into more things. It can induce more dipoles. It can have stronger dispersion forces. And that's the case. If we think about this gray line here as the surface area is a little bit bigger between these two molecules. It's a little bit bigger between these two molecules. So if you increase the surface area, you're going to increase the dispersion forces. You're going to increase the attraction. You're going to increase the likelihood that it's going to move on to be a liquid or a solid at room temperature. Dipole-dipole is just one step up. If you remember that we talked about molecules that are polar, that means they have a standing dipole. They don't have to wait to bump into something to get a dipole temporarily. They have a dipole all the time. So if we have a polar molecule, not a polar bond, but a polar molecule, then they have that standing dipole. They're just waiting to bump into something else that already has a dipole. And so if you don't have to wait for a dipole to be induced, if this is always on, then the attraction is just a little bit stronger. And so in the case of HCl gas, we always have a dipole. We always have a dipole. This negative side is going to be attracted to the positive side all the time. It doesn't turn off. And so HCl gas molecules are much more attracted to each other than, say, Cl2 gas molecules from one of our previous slides. The next step up in strength is ion dipole. So that's taking something that always has a dipole, a standing dipole, and then interacting with an ion. So if you think about how salts dissolve in water, we just kind of said it happens in Gen Chem 1, but we never described how. The how is because the water molecule has a standing dipole, so one side of the water molecule is a little bit positive, one side's a little bit negative. If you dissolve sodium chloride, the sodiums become Na pluses, the chlorines become Cl minuses. Well, the positive side of a water molecule surrounds a negatively charged chlorine ion. The negative side of the water molecule can surround the positively charged sodium ion. And they form these little cages around the ions. So that's stronger than the dipole-dipole interaction, because now we have a dipole and we have that charge, we have a full-on charge on an ion. The strongest is the hydrogen bonds. It's the strongest on this scale because we're only talking about intermolecular forces. Hydrogen bonds are not covalent bonds. We have some examples of covalent bonds in here. They're solid lines. Those are intramolecular forces. The hydrogen bonds that we're talking about are these dots. Dot, 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 dot. These are weak attractions between two different molecules. It's a special case of the dipole-dipole interaction. It's a special case because we have to have A hydrogen that is covalently bonded to a nitrogen, an oxygen, or a fluorine on one molecule. And on the other molecule, we need to have something with at least one lone pair. And so we will show you some examples that fit those specifications the next time we get together to reinforce what is a hydrogen bond when you start to look at some of these molecules.